Hello friends, Jim here in yet another video discussing oscillatory systems of our planet. This video we're going to discuss the Arctic Oscillation. The Arctic Oscillation, the AO, sometimes referred to as the Northern Annular Mode or Northern Hemisphere Annular Mode, NAM, usually it's AO, is a weather phenomenon at the Arctic and Antarctic poles north or south of 20 degrees latitude. That's a wide range. Actually, I think it's a typo. It should be like 60 degrees. Anyway, the index varies over time with no particular periodicity and is characterized by non-seasonal sea level pressure anomalies of one sign in the Arctic, balanced by anomalies of opposite signs centered at about 37 to 45 degrees north. The NAO is a close relative of the AO and may be coupled together. There is debate over whether one or the other is more fundamentally representative of the atmosphere's dynamics. The AO appears as a ring-like or annular pattern of sea level pressure anomalies centered at the poles. The presence of continents and large land masses disrupts the ring-like structure at the Arctic pole, while anomalies surrounding the Antarctic pole are nearly circular. The difference basically is the Arctic is an ocean surrounded by landmass, whereas the Antarctic is a landmass surrounded by ocean. The AO is believed by climatologists to be causally related to and thus partially predicted of global weather patterns. NASA climatologist Dr. James E. Hansen explained the mechanism by which the AO affects weather at points so distant from the Arctic as follows. Okay, so here's Dr. Hansen. The degree to which Arctic air penetrates into middle latitudes is related to the AO index, which is defined by surface atmospheric pressure patterns. When the AO index is positive, surface pressure is low in the polar regions. Let me repeat that. When the AO index is positive, surface pressure is low in the polar regions. This helps the middle latitude jet stream to blow strongly and consistently from west to east, thus keeping cold Arctic air locked in the polar region. When the AO index is negative, there tends to be high pressure in the polar region, weaker zonal winds, and greater movement of frigid polar air into middle latitudes. So this helps explain why the statement about reaching 20 degrees to 90 degrees in both hemispheres. It's the effect, where it's found, where the actual, and this video is looking at the AO, so I'm not looking at the Antarctic. But the AO, when you look at what's going on within that, it's from 60 to 90. But this is obviously explains why they look at from 20 degrees on up to 90 degrees is because of the impact, how far it reaches down. Over most of the past century, the AO alternated in positive and negative phases. Data using a 60-day running mean has implied the oscillation has been trending to more of a positive phase since the 1970s, though it has trended to a more neutral state in the last decade. The oscillation still fluctuates stochastically, that means random, between negative and positive values on daily, monthly, seasonal, annual timescale, although meteorologists have attained high levels of predictive accuracy with shorter-term forecasts. The correlation between actual observation and 7-day mean global forecasting system, or GFS ensemble, AO forecast is approximately 0.9. Pretty good. Now, I want to, before I talk about this last paragraph, I want to discuss what's meant by 60-day running mean. What that means is you collect data, let's say a temperature. Okay? In this case, maybe they're looking at measuring air pressure at a location. 60 days, you measure an air pressure. So you calculate the mean for the air pressure for those 60 days. For the 61st day, okay, so for the first one, you go from 1 to 60. For the 61st day, you go from 2 to 61, and you measure the air pressure and get an average. The next one, you go from 3 to 62, get an average. 4 to 63, get an average, etc. That's what they mean. You do the same thing for the 30-day running average. 1 to 30, then 2 2 to 31, 3 to 32, etc. 90 day. You get the idea. That's what's meant by running mean or running average, is that you go over the prescribed number of days and you take the mean of your measurements for that time period. And it keeps moving day by day where we look at the previous 60 days. This is what a lot of climate analysis is all about, is that we're doing running averages all the time. So back to this. The zonally symmetric seesaw between sea level pressures in polar and temperate latitude was first identified by Edward Lorenz in 1951 and named in 1998 by David Thompson and John Michael Wallace. NSIDC, National Snow Ice Data Center in Boulder, Colorado, describes the effects of the AO in some detail. In the positive phase, higher pressure at mid-latitudes drives ocean storms farther north, and changes in the circulation pattern bring wetter weather to Alaska, Scotland, Scandinavia, as well as drier conditions to the western U.S. and Mediterranean. Starting to sound like a part of the NAO, is it not? In the positive phase, frigid winter air does not extend as far into the middle of North America as it would during the negative phase of the oscillation. This keeps much of the U.S. east of the Rocky Mountains warmer than normal, but leaves Greenland and Newfoundland colder than usual. Weather patterns in the negative phase are in general, quote unquote, opposite to those of the positive phase. Climatologists are now routinely invoking the Arctic Oscillation in their official public explanation for extremes of weather. Following a statement from NOAA, National Oceanic Atmospheric Administration, National Climate Data Center, the NCDC, stated of climate December in 2010, which uses the phrase negative Arctic oscillations 4 times, is very representative of this increasing tendency. And a quote from that report. Cold Arctic air gripped Western Europe in the first 3 weeks of December. 2 major snowstorms, icy conditions, frigid temperatures wreaked havoc across much of the region. The harsh winter weather was attributed to a negative Arctic oscillation, which is a climate pattern that influences weather in the northern hemisphere. A very persistent strong ridge of high pressure or blocking system near Greenland allowed cold Arctic air to slide south into Europe. What does that sound like? It sounds like the negative NAO, does it not? Europe was not the only region in the northern hemisphere affected by the Arctic Oscillation. A large snowstorm, frigid temperature affected much of the Midwest U.S. December 10th and 13th. So let's look a little more detailed at the events of 2010. Further quite graphic illustration effects of the negative phase of this oscillation occurred in February 2010. In that month, the Arctic Oscillation reached its most negative monthly mean value at about minus 4.266 in the entire post-1950s era, the period where accurate record keeping began. That month was characterized by 3 separate historic snowstorms in the mid-Atlantic region of the U.S. The first storm precipitated 664 centimeters on Baltimore, Maryland, February 5 to 6, and the second storm, 50 centimeters on February 9 to 10. In New York City, a separate storm deposited 53 centimeters. 10 millimeters equals a centimeter, so I'm just dropping the 0 and changing the first M to a C. Another snowstorm swept Catalonia, as well as neighboring French departments like Languedoc-Roussillon and Midi-Pyrenees on March 8, depositing 60 centimeters of snow in Girona. This kind of snowstorm activity is considered to be highly anomalous and as extreme as the negative AO value itself. The greatest negative value for the AO since 1950 in January was minus 3.767 in 1977, which coincided with the coldest mean January temperatures in New York City, Washington, D.C., Baltimore, and many other mid-Atlantic locations in that span of time. And though the January AO has been negative only 60.6% of the time, which means been positive 39.4%, between 1950 and 2010, 9 of the 10 coldest Januaries in New York City since 1950 have coincided with negative AOs. The Arctic Oscillation refers to an opposing pattern of pressure between the Arctic and the northern middle latitudes. Overall, if the atmospheric pressure is high in the Arctic, it tends to be low in the northern middle latitudes, such as northern Europe and North America. If the atmospheric pressure is low in the middle latitudes, often high in the Arctic. When pressure is high in the Arctic and low in mid latitudes, that is when it is in its negative phase. In the positive phase, the patterns are reversed, that is, it's low in the Arctic, high in mid latitudes. Meteorologists and climatologists who study the Arctic pay attention to the AO because its phase has an important effect on weather in northern locations. The positive phase of the AO brings ocean storms farther north, making the weather wetter in Alaska, Scotland, Scandinavia, and drier in the western U.S. and Mediterranean. I've already touched upon that, but it's worth repeating. The positive phase keeps the weather warmer than normal in the eastern U.S. and makes rain colder than normal. In the negative phase, the AO, the patterns are reversed. A strongly negative phase of the AO brings warm weather to high latitude, cold, stormy weather to more temperate regions where most people live. Over most of the past century, the AO alternated between positive and negative phase. For a period during the 70s to mid-90s, the AO tended to stay in its positive phase. However, since then, it's again alternating positive and negative, with the record negative phase in the winter of 09-10. So here we go. Now we get into, so here's the positive phase. Higher pressure confines the cold air to the Arctic. Negative phase, lessened pressure can't confine the cold, so it starts to spill out from the Arctic. So in the positive phase, we have a strong low and high air pressure at high middle latitudes. Extremely cold air confined to the Arctic, warm middle latitude, strong vortex. You've heard of the polar vortex. Okay. So when we hear about, the polar vortex weakening and spilling further south, that's a couple of things. That's due to the negative phase of the AO, but it's also due to the pressure gradient not being as well defined as it has been historically, so that it's easier to follow the pressure gradients kind of spilling downward, but it also moves in a slower manner and it lingers longer because the pressure gradient is not as strong as it used to be, so the air movement will not be as quick. The stronger the gradient, the faster the airflow is when looking at pressure gradient. The less the difference is, it's going to be a slower mover. So now when it's in the negative phase, the pressure system weaker. Cold Arctic air will spill into middle latitude. Warm middle latitude air moves into the Arctic, and you have a weak vortex. So on the left, we see the effects of the positive phase of the Arctic Oscillation. Low pressure in the Arctic. Okay. And what do we see? We see storm tracks nailing Ireland, the UK, and so on. It's warm and wet over Scandinavia, Iceland. Cold over here. Dry in the Mediterranean. Effects of the negative phase of the Arctic Oscillation. You have high or low pressure in the Arctic. That is, low pressure is not as low. And then what happens is you get a spilling out of the cold air. So less cold stratosphere. Okay? So what you need to keep in mind is that when we say low pressure, it's all relative. Sometimes the low pressure is not as low. Still be low, but it will be higher relative to the other situation. But basically, in the positive phase, the cold is confined to the polar region. In the negative phase, it spills out. That's kind of what the take home is. And that will then affect the temperature and precipitation pattern as I have described in the previous slides. Again, this just shows you, again, with positive Arctic Oscillation, you can see that. Now look here, stronger lows, stronger highs. Weaker low, weaker lows. That sounds like the NAO is in the positive phase, and the NAO is also in the negative phase. Get to that in a moment. Okay, so this once again is just kind of trying to bring it all together. I apologize, that's not as readable as I thought it would be. Okay. Um, Negative Arctic oscillation, you have a higher pressure here. But see, what happens is with the lower pressure, you create a stronger cyclonic flow. Higher pressure, you actually, it is still a low pressure, but it's higher in the negative than it is in the positive phase. -4 is more negative than -2, basically. So because the air pressure is higher, the cyclonic flow is not as strong, which is how it spills out. This is a lower air pressure, so it is create a stronger cyclonic flow, which is why the cold air is trapped. That's the key here. So when you see, the positive Arctic oscillation, the lower pressure here is stronger than here. The stronger low pressure system leads to a stronger cyclonic flow, which traps that cold air. Not as low, the flow is not as strong, and it starts to spill out. That's really what's going on in it from an atmospheric aspect. I hope that makes sense and clarifies any confusion that might be. And again, you get the stormy track and stuff like that. So you're gonna have, this is warmer than usual, colder than usual, and the flip flop, colder than usual, warmer than usual, and it flip flops between the negative and the positive, as well as the changing precipitation patterns. Wetter than usual, okay, and then drier than usual as well. So here's some wetter than wetter than usual, and then where it's dry, it will be drier than usual. So warmer, this is cooler. You get the idea. Again, you can just go back to the slides there where it describes what's happening weather-wise. On the left is the positive phase. Very strong low pressures. You have a stable polar vortex. The jet stream is contained. When the low is not as low, the polar vortex is not as strong, so it gets a little wavy. And you can see starts dipping down. Here's that blocking high. So air pressure and winds around the Arctic switch between the two phases and contribute to winter weather patterns. So this is the negative, that's the positive. On left is positive, right's negative. So just to back up here, okay, the negative phase of the Arctic, the patterns are reversed. Okay, so when the pressure is high in the Arctic, low in the mid-lat, it's in the negative, and then it's reversed in the positive. So the positive phase brings ocean storms farther north, making the weather wetter in Scandinavia and so on. And then the negative phase, you get the reverse. So going back to this particular diagram, the positive is going to bring the storms further north. So you get wetter. Okay? So it's warmer and wetter, but it's cooler down this way. The negative phase here is going to be colder but drier. Right? Remember, warmer air holds more moisture. So that's basically what the difference is between those two. Okay, so here is looking at it from looking down at the pole, if you will. And on the top, we have the AO, positive and negative, and on the bottom, we have the NAO, positive and negative. We recall that the positive phase of the NAO has a stronger high in the Azores and a stronger low in the Icelandic region, and it's weaker for both pressure systems during the negative phase. And what do we see here? Strong, we have a lower pressure here. There's still lows, but this is even more negative, if you will, lower air pressure, so that we get strong cyclonic flow and get a more northerly track. And that's with the positive. And you can see here, wetter but warmer, and it's drier as you go into the Mediterranean. During the negative phase, we get the dip down. So now it's colder, right? Warmer, colder, wetter, drier. You can see how it flips. Drier, wetter. So the cold Arctic air dips down. Cold Arctic air dips down. Here, the cold Arctic air is contained. So it's warmer here, colder here. I really like this graph because it shows how these two are tied together. Usually when the AO is in the positive phase, so will the NAO. Right? See how they're both wetter, wetter, drier, drier. Okay, you see how they are in agreement, and when they both tend to be in the negative phase. So you get drier conditions and drier conditions, wetter conditions, wetter conditions. So they are really strongly coupled together. I said, I really like this graphic because it shows what's happening. It gives you the summation as well as showing the coupling that goes on. So we have here Arctic Oscillation, North Atlantic Oscillation, both in a positive mode. Arctic Oscillation, North Atlantic Oscillation, both in negative mode. Okay. Strong subtropical high pressure systems, the Azores. Strong subpolar low, that's the Icelandic. Okay. So you get a strong polar vortex, very strong cyclonic flow. And then you have the Arctic air is constrained, so the jet stream is more northerly and more zonal, more of a zonal flow that brings mild wet conditions to, where's the cursor? Mild wet conditions to Northern Europe and Scandinavia, and also mild and dry conditions to Europe and the Mediterranean, and about to be video bombed here in a moment. You want to say hello? Say hello. Say hello. Just don't step on any keys. My cat here. Say hello. Look at the camera. Anyway, oh no, don't rub on the computer. Come on. I just got the damn thing fixed. Oh, that was coordinated. She almost fell off the table. Okay. Excuse me for a moment. I have to put her down on the table. Off the table. Come on. Come on, down you go. Okay, there we go. That's the feline. The feline and the canine. So where were we? Oh yes. We look at the contiguous U.S. here. It's mild and wet. And here's the jet stream. During the negative oscillation, okay, these two pressure systems weaken. So the subtropical high weakens, these subpolar low weakens. The polar vortex weakens. So the cold air is not as contained. It starts dipping down, and when it dips down, it brings the cold Arctic air with it. This is what's been happening lately. But also with the overall warming of the ocean and the atmosphere and stuff like that, the gradient is less. So not only does it dip down, it slows down with its travel so that it lingers more. And if it's bringing precipitation, it's going to linger more and bring more precipitation. You also note that the Arctic air invades the south, okay? But you also notice what the jet stream is doing. The jet stream becomes more meridional in its flow. Right? Zonal is just blasting across west to east, but it becomes more meridional, becomes takes on a more north to south, south to north, right? South to north, north to south flow, kind of more meandering, more meridional. Look what's happening to the storm track. It's further south over southern Europe and the Mediterranean. It's cold and dry over northern Europe and Scandinavia. Mild and wet during the positive phases, mild and dry. Cold. So southern Europe goes between mild and dry to mild and wet. Northern Europe, Scandinavia goes from mild and wet to just cold and dry. So between these two graphics, yeah, this one shows what's going on with the AO, but these two graphics really help solidify what's going on with the AO and how it is coupled with the NAO. And here's some AO indices here, going from about 1900 to the latest about 2016 or so. And values up here are in the positive, and this is the negative here. And again, you get the smoothing, running averages here. So you can see how we've kind of gone into a positive phase, and it kind of went back and forth between positive and negatives. Here's another look at it, looking at the NOAA data, the National Climatic Data Center, the NCDC. And again, then this is looking at from 2000 to 2015, 2016. So if you look at it, you can see how the 2000 starts about here, and you can see this is about where it's starting. So that's about 2001. Oops, went the wrong way. About 2001, and here's that positive phase there. This is a side-by-side comparison. DJF is December, January, February. And we're looking at the Arctic Oscillation and North American temperature. So the upper panel is the oscillation. This is the indice, positive and negative here. And then here's the temperature difference anomaly. And basically, we're seeing that when it's warm, it correlates to a positive phase, and when it's cold, to the negative phase. Again, you see the cold and the negative phase of warm. In the positive phase, just like here. Okay, so I guess I could have included this with my rotating systems, but kind of consider this as a review. Cyclones are low pressure systems or circular weather patterns that rotate in a counterclockwise direction in the northern hemisphere, clockwise in the southern. Okay, we discussed this in my rotating system. Cyclone air moves upwards in the center, bringing stormy wet weather. In the Arctic, cyclones occur year-round, but they tend to happen more in certain places depending on the time of year. Semi-permanent lows in the Arctic include the Aleutian Low. I discussed that in relation to the PDO. A low-pressure center that experiences many cyclones and storms in the winter. And the Icelandic Low, a low-pressure center located near Iceland. Anticyclones are opposite of cyclones, high-pressure systems that rotate clockwise direction in the northern hemisphere, counterclockwise in the southern hemisphere. Anticyclone, known as the Beaufort High, recurs year after year, sitting over the Beaufort Sea, Canadian archipelago in winter and spring. Anticyclone also frequently appears over Siberia, known as the Siberian High. And so you have polar lows, okay, are small intense cyclones that form over open ocean during the cold season. From satellite imagery, polar lows can look much like a hurricane with a large spiral of clouds centered around an eye. For this reason, it's sometimes called Arctic hurricanes. Polar lows range in size from about 100 to 500 kilometers in diameter. Wind speeds average around 80 kilometers per hour, and can occasionally reach hurricane strength, 64 miles per hour, 72 miles per hour. That would be about 110 kilometers per 110, 120 kilometers per hour. Well, polar lows tend to form when cold Arctic air flows over relatively warm open water. And with the sea ice dwindling, there's more of that happening. The storms can develop rapidly, reaching a maximum strength within 12 to 24 hours of formation, but they can dissipate just as quickly, lasting on average 1 or 2 days. Weather maps show the circulation pressure patterns over one or several days, but maps of sea level pressure can also be averaged over several months or years to show the average circulation patterns in the atmosphere. These average maps remove some of the variability caused by day-to-day weather changes, instead showing longer-term patterns that can affect weather and climate both within and outside the Arctic. Researchers compare the relative strength of semi-permanent highs and lows and report these comparisons in indices such as the NAO and the AO. These indices have been linked to variability in temperature and to sea ice conditions in the Arctic. And here's some examples of semi-permanent pattern. The Aleutian Low I've discussed. We've been discussing Icelandic and Azores High, the Siberian High, the Beaufort High, the North American High. So if you wish, you can pause the video and read through this. But I just put this in here for completeness sake. To sum up, the AO and the NAO are basically coupled together. When it's in the positive phase, strong polar vortex means you have a very strong low pressure system containing the Arctic air here. That leads to mild conditions that tend to be wetter for Northern Europe and Scandinavia, mild and wet for the most of the US, for example. Very strong Azore high, very strong Icelandic low. Mild and dry for Southern Europe and the Mediterranean. When both go into the negative phase, it's still a low pressure system, but it's a weakened low pressure system. So the cyclonic flow is not as strong, does not contain the cold polar air as readily. So now it dips down. And it dips down, it brings cold air to the US and Canada. This is a blocking pressure system here. And we now get cold conditions over Northern Europe and Scandinavia. And instead of being mild and dry over Southern Europe and the Mediterranean, it's mild and wet. So this is what happens, and they are coupled together. That's basically what goes on in the oscillation, is this changes from very strong low to a weakened low, is really what it is. And a weakened low means it has higher pressure. The stronger the low, the lower is the barometer reading. So a weakened low, it means it has a higher reading. It says, think of this as like, this is -4 and that's -2. More negative, it's lower. And then, of course, this is another way of showing, what happens here. You can jump in. This is looking straight down on the pole. So there you have it. There's the Arctic Oscillation. You can always go back and review the slides. Watch the video several times to maybe pick up a few things and get the first go around, whatever. But there you have it. So thank you for your time. And up next will be the AMO. Hey folks, this is Jim here reminding you to please subscribe to my channel and please share my videos with others. Also remember to click the bell so that you know when I drop in a new video. I also ask that you please consider becoming a patron of my channel and support the work that I do by going to patreon.com/Science Talk with Jim Massa, each word separated by an underscore, and becoming a patron. It's asking for as little as $3 a month, cost of a cup of coffee, to support the work I do and keep my informative videos coming your way. Thank you for your support.